Hello everyone, my name is Vladislav Palfy. I'm the Director of Application Engineering at OneSpin Solutions, and I'm delighted to be here with you today to talk about how a powerful FPGA verification platform can help you achieve the goal of the day, which is the mission to go to Mars. I will just quickly lay out the agenda for today. So I will cover a little bit about OneSpin as a company, talk about what formal verification is, and then we'll dive right into the technical specifics, which are automated formal checks and how they can help impact your FPGA flow. I will share a case study with you, and in the end I will cover the topic of why it is very important to make sure that equivalence checking is also applied for FPGAs. So a little bit about OneSpin. As a company, we have a focus on IC integrity verification solutions, where we help our customers develop reliable, safe, secure, and trusted integrated circuits. And most of the challenges we target are critical verification challenges. We have been around since 2005 with a worldwide presence and a growing team, and our technology is extremely mature and has been validated on hundreds of different projects and tapeouts. We also have a very steady growth and an increase in the number of customers worldwide, and we always like to explore new product areas and opportunities. Our story is based around three pillars, which are functional correctness, safety, and trust and security. The topic of today's talk is going to focus mostly on functional correctness. So, what is formal verification and why should you care? Let's start by comparing it to simulation. So what you're used to doing in simulation is you will check a specific sequence of states, and you do this by writing stimuli and trying to move throughout the design states and hit as many of them as you can. Formal is, on the other hand, based on mathematical proof reasoning. This means that you, first of all, don't have to worry about stimuli because the formal engines take care of this. And something else formal will do is, unlike simulation that goes through a certain sequence, it will cover all possible scenarios for every state, which is what makes formal exhaustive and really good for finding corner case issues. What this means to your project cycle is that if you use a formal platform, which is highly automated and has specific apps that can help repetitive processes, you will be able to apply verification early on in the design cycle, which will do the famous shift left turn, which in turn eliminates the need for more complex testing down the road and will enable you to have an earlier tapeout. Now let's talk about how these automated formal checks can impact your FPGA flow. And if we look at a typical FPGA flow and what RTL issues can happen in it, while you'll do your planning, requirements, and conceptual design, we won't cover that today. What we will cover is two different things. So what do you do when you have a detailed design? And this will be the topic of this chapter. And later on, we'll move to implementation and equivalence checking. And I will try to demonstrate to you why it's really important that you do these two steps before you actually program your device. So this got me thinking a little bit, and I wanted to make an analogy of what the usual FPGA implementation flow looks like and what you're trying to do today. So let's jump into it, right? So this guy here on the bottom is you, the designers and verification engineers. And then you have Mars, the red planet, obviously. You have the Nokia satellite beaming you the information. And here you have your happy customer in the rocket, that you sent to Mars. Right? So let's say that we consider the current verification flow that many FPGA people still use. This would be equivalent to you asking, I wonder if the spacewalk cable should have been verified before we launched, which probably will prompt your customer to react something like this, and which would in turn make your competition, or in this case, the people on Mars that are waiting for you, well, they would probably laugh at you. So why am I saying all of this? Well, it's because the current FPGA flow is very similar to what I just shown. You have your detailed design, you do some implementation, put it on the board, and then you go off to the lab and you spend some hours on implementation, you spend an hour to program the device, and then you spend hours to days debugging on the actual board before you fix the one RTL issue, and then you start over. Each issue will take at least one iteration to fix enough, if not more, and this will just waste loads of time. And to illustrate a little bit, we have a small example of a Xeon 3 processor, 220K lines of code, and it takes roughly an hour to get through one iteration that you can get on your board and debug and fix your RTL. This does not include debugging time, by the way, so this could be days essentially. And what can these bugs be, right? Well, it can be a numerous amount of structural issues, unsafe HDL activation issues, like let's single out a few: signal truncation, accessing array out of bounds. You can hit deadlocks in your transitions and FSMs. It's a really big variety of issues. It's very easy to introduce them by accident, almost impossible to detect manually, and they're really hard to debug on an FPGA board, which can have a massive impact on your project schedule. And this being a hackathon, 24 hours is kind of a time crunch. So what am I going to propose to you to resolve this? Well, I'm going to propose automatic inspection of RTL. This means that you will be able to read your RTL code into the OneSpin tool, do a quick setup, and then you will be met with a range of safety and activation checks, what we call auto checks, that utilize the formal engines, which means the tool will generate stimuli automatically, which you can then debug interactively on the code. So you will be able to catch design issues very early on in an automated fashion. The full power of formal is there, much more than linting and much faster than simulation. There is no need for you to write any assertion stimulus, test benches, anything. So the idea is that this will significantly improve your design schedule. And to talk about one real-world example, there was a safety automotive design that was held up to 4 days for a simulation synthesis mismatch, and it really took just minutes to solve it with our tools here. So how does our FPGA flow look now? So it's a little bit different than the previous one, right? And what I would claim here is that you should be doing automated inspection on the design and fix issues here. This takes minutes, right? Which means that you will be able to find multiple issues at the first iteration, not just one, using OneSpin 360 DV Inspect, which is the name of the tool. And only when you're done with this and you have no issues, you will go to the implementation, which still takes hours, of course, and you will program the device, which still takes hours. But your debug will now take minutes because you would have eliminated all of the issues using automatic inspection. So there's really loads of savings here. You will cut down the number of implementations and these long cycles that you need to go through. Debugging will be much easier because you will have a proper debugger and you will not have to figure stuff out on the board itself. So there's really massive savings in the project schedule there. And coming back to our Xeon 3 example, for the most important checks, right, which we call safety checks, which will be simulation synthesis mismatches or checks which will cause your simulator to just fault out, well, these will take you probably around 10 minutes for this design. And you see, for 5 seconds, for example, we have found 16 issues on this design. And if you do want to go a little bit deeper to analyze also stuck signals and some things that are maybe superfluous in your design, this will take you up to an hour for this particular processor. And the range of issues you can find is really large. So these are not even all the checks listed, and you don't have to read from the slide here. We can always share these slides with you. But there's a myriad of checks you can run, and these are all automatic. So whether it's parallel through cases, write and read-write races, negative division, arrays out of bounds, making sure you have no dead code, making sure your FSMs behave like they should behave and that there is no deadlocks or live locks, this is all there for you. However, this is just one portion of things you can do with formal tools and with the OneSpin offering. And this is probably the most important thing you start with, but I also want to share some other capabilities which you probably won't have time to work with during the hackathon, but they're really important to note. So what else could you be doing? So let's start with formal apps. What we do with apps is that we take tasks that are very repeatable and that are highly automated, and we package this for you so that it's user-friendly and it's very easy for you to apply this to your designs. And these range from formal verification IPs to making sure your register maps are correct through connectivity checking. And for example, X propagation analysis, where we help our customers make sure that no X's can influence any design functionality, because these can be extremely difficult problems to debug and even identify in the field. But you could also be using the power of formal to do functional verification of your design by writing your own assertions. In addition, another unique capability we have is to turn any formal trace into a directed test. So we allow you to generate a test in any language and just feed it into your simulator, whether it is because you want to prove to the simulation people that this behavior is indeed happening in the design because it's a corner case, or because you want to have a set of directed tests that you can reuse in any way. But this is all there in the tool for you, along with a very powerful debugger. And once you have all these assertions written, the question is always, like with any verification, how well did I do? Right? When am I done verifying? And that's always been the case, that people usually say that your verification is only as good as your verification plan. However, we went a step further and we have developed a very unique mutation coverage model, which really helps with identifying verification holes. So the challenge is that you need to determine which part of your design is not covered by the assertions you have written. And this is where traditional cone of influence methods are very inaccurate. And with the OneSpin Quantify app, we provide a very precise coverage algorithm, and we also guide your assertion development towards closure. You can also use it effectively as a bug hunting mechanism, and you can use it to detect unreachable and over-constrained code, which is extremely important. The way we do this is that we have internal methodology which doesn't change your design, works on a model, and it will run your assertion set against all possible mutations in the code. And what comes out is a very telling view that will distinguish code which is covered by the assertions from code which is not covered, which will guide you which assertion to write next. But we will also show you which code is dead and which code is dead due to a user constraint, which is usually a problem that you want to uncover early on. Now, all of these solutions are integrated in one flow, and we will provide a complete coverage, closure, and verification sign-off with this. What we have worked on is a special app that will help connect your verification work in formal with any simulator and planning tool. So we will be able to export all the formal data to your verification plan of choice, to your coverage database of choice. We can help you close coverage by running formal first before simulation. And all of this leads to a complete verification sign-off. Our solution is completely independent of any vendor, and it can integrate into any simulation flow that you might have. Let's now go back to our initial topic after this quick intro in what else is available, and go back to automated checking. So I have prepared a small case study for you, which was done on a real FPGA board, RT. And I'm going to show to you how we have identified an issue that didn't come up in simulation, but only came up when we loaded the design on the board. So the design architecture will keep it as a black box, but what the functionality should be is that you have two switches, and if you push one switch, you will have the LEDs on the board turn blue. And if you hit both switches, they should be turning green. And before we went to the board, we simulated this a little bit, and you can see the behavior here. We flip one switch, and as long as some register values in counter have the same value and one switch is on, it goes to blue. Same thing for switch number 2. It goes blue once these two registers have the same value. So one switch makes it blue, works fine. And then we also tested both switches being on, and you can see that the LEDs turned from red to green. So we were happy with our little simulation experiment. using the usual FPGA flow. And then we went to the board. So I already mentioned an FPGA from Xilinx in this case has 4 LEDs which we played around with and some switches. So we then proceeded to do the on-board test. And once we did that, we actually identified that at a certain time point when you flip both switches, the LEDs do indeed turn green, but then they actually turn blue in the next clock cycle, which is a violation of the specification. So what is there left for us to do? Right? So we didn't get any warning message or any error message from the synthesis tool. We didn't see anything in simulation, and it's a difficult issue to spot. So, JTAG debugging, well, no, I think not, because if you remember what we talked about in the first part of the presentation, there is a better way to do these things, which is automatic formal checks. So by integrating the DV-inspect tool in the design flow, what we did is what we mentioned before. Right? Before going to the board, we actually did inspect checks on the RTL itself. So switching over to the OneSpin tool real quickly, I'm going to show you what we did. So I have the design read in here into the OneSpin tool, and I'm going to go to the auto checks tab that hosts these inspect checks. And as you can see, we have 2 read-write checks that the tool identified. It's a race check, because in fact we do have a difference between simulated and synthesized behavior, and this could be it. So I'm going to go ahead and run these checks for a second. So it's quite a deep design. You will see that the tool progresses quite fast through the states. So the number in the bracket you see here is actually the number of states after reset, which is in no way small. Right? So you see we're already 2600, and bam, there we go. We have a failure. Right? So the other check is still running. Let's give a second to this one to finish as well, because I ran about at the same time. So we will see that both of the read-write checks are actually failing. Right? So what we can do now is we can debug this failure. And we will then see a debug trace, which I will zoom into. And let's see a little bit what's going on. I'm going to add one signal here, because this will help our debugging. And the signal I'm going to be adding is actually the LED vector, which will show us the color. Just expand this a little bit. So what we see here is that there is a reported failure here in red in this clock cycle. And if we look at what happened, so both switches have been turned on, and in this clock cycle we would expect the result to be green, but it's actually blue and only goes green in the cycle after this. So we can then go ahead and debug and fix this issue, which I'm not going to do, but this is clearly a violation of a read-write condition, because we have 2 processes writing into the same space. And OneSpin has identified this, as you've seen, within seconds, and with a very deep fail. Okay, and moving back to the slides now. So as I mentioned during the debug session, there are in fact 2 processes that are running in parallel to update the 2 registers. And it wasn't really clear whether there is a read-write trace condition, because the way the code is written and the way the FPGA board operates are actually different. And that means that we had a read-write race situation, which simulation didn't catch. It was very difficult to debug it in the board, but we managed to prove it with a very simple and very quick inspect auto check. Okay, so I would then like to move to the last technical topic of the speech, and this is the importance of FPGA equivalence checking. And you probably have heard about equivalence checking. It's not an unknown term, but it has a special place in FPGA. Again, we consider this part of functional correctness. And if we go back to our FPGA design flow view, well, this now targets the implementation. So what is it that we do here with equivalence checking? Well, when you take your RTL code and you synthesize it using the synthesis tool into a netlist, you want to make sure that these two are indeed behaving the same. And this is where OneSpin 360 EC-FPGA comes into place. So I'm going to take you a little bit through the advantages of using this kind of verification tool. And let's start by what it means to have full coverage. Because the tool is formal, we will again compare it to what a simulation equivalence check does, and it's basically the same as we mentioned in the first part of the talk. So if you simulate, you're going to just try to run some similar values to both the RTL and the netlist and compare their behavior. But since we are doing formal, we're going to go through all the possible combinations of sequences, right? So we will really be able to determine whether the designs operate the same for any possible input combination. And in case they don't, you want to be able to determine this. So if you get a non-equivalent compare using OneSpin, well, you will be able to debug this in the tool and try to find out the reason for the designs not behaving the same. And why is FPGA equivalence checking so important? Well, you might be used to the ASIC world, and you think that you could do the same with the same tools for FPGAs, but that is very far from the truth, to be honest, because if you look at a typical FPGA, and they're getting more and more complex, there are numerous optimizations that the synthesis tool will do. And some of these are FSM re-encoding, triple module redundancy, RAM implementation of SLRs, you name it. Each next generation of FPGAs will result into more and more optimizations. So what this means is there's not always a one-to-one mapping, right? So of course, with our tool, we also try to get as many combinational mappings as possible. But since this is an FPGA, it's not always going to be possible. So if you have some re-encoding or retiming, you cannot get the one-to-one mapping. So you have to really understand what these sequential optimizations mean. And this is what we do really well with OneSpin EC-FPGA. Now you might say, why would I have to do this if I trust that the synthesis tool works correctly? And yes, you might have a point there, but consider this, right? It's really not easy for the vendors to verify and validate every possible combination of optimizations with every possible type of RTL. The designs are getting more complex, the design styles are different, and this is really something that the synthesis vendors also encourage you to do. And I'll give you one example on a Xilinx Kintex board, quite a large board with nice percentages of utilization, with a mixed signal VHDL Verilog design, which it took 5 to 6 hours to synthesize on a 32-core server, so quite big. And the design was already running in hardware, but EC-FPGA identified that an FSM encoding that was supposed to be one hot was wrongly encoded, and this led to a corner case bug that would be almost impossible to find during final testing. So the reason why OneSpin is able to handle these things and your typical tools for ASIC are not, well, it's because of this, right? We are collaborating and partnering with FPGA vendors. They're a long-term customer of OneSpin, and it's kind of a dual relationship, right? They are customers, and their customers are our customers, but we also partner with them in development. So when there is a new FPGA board coming out, the tool vendors will actually work with OneSpin to validate if their transformations and new algorithms work correctly. And we have a very nice partnership with Intel, Altera, where we worked on their latest and greatest Stratix 10 and Aria 10 boards. So this is a really exciting project, and we are looking forward to continuing this collaboration, of course. And of course, the more complex these FPGAs become, the more complex use cases they have. Take 5G, for example, or take your mission to Mars, of course. Or, automotive as well. So this is why it has become increasingly important to also have some trust in the flows. So what we have done is we have invested heavily into certification, And together with our EC-FPGA platform, you can get a tool qualification kit that covers ISO 26262 and some other standards. And this will really significantly decrease the time the user needs to qualify their flow, because we provide all the necessary information there. We're also dealing with DO254, of course, and you can see a quote here from our customer Hitachi, who actually used this in a project. Now, one interesting aspect of EC-FPGA, which was not really considered that much before, but is becoming increasingly important, is that we could actually detect functional Trojans. Now, you've seen in our pillars there that OneSpin also deals in trust and security verification. So this is just one example with one tool. We have many other tools, but when it comes to FPGAs in particular, it's really easy to detect whether a synthesis tool or a manually edited netlist contains some functionality that the original RTL or some other netlist you compare it to didn't contain. And since this is exhaustive formal technology, we guarantee that we can reliably detect any functional Trojans with trigger conditions that simulation would never find, mostly because a human would never think that this is the pattern that I need to send to both designs in order to uncover something that I don't even know it's there, right? So this is really something that is bringing lots of advantage in today's uncertainties, and helping customers make sure that their designs do only the intended things they're supposed to do, and nothing more and nothing less. And of course, any company is proud of its customers, and we really are proud to be working with so many great companies, of course Nokia and Altera, Intel included. And I'm going to just mention some of the success stories here that we are proud to share with our customers, and proud to help them achieve better quality of their designs and get rid of bugs early. And then I would like to actually leave you with a recent study which says that 83% of FPGA design projects have non-trivial bugs that escape into production. And we would really like to help you save the day, help you reach Mars today, and make sure that your designs are bug-free, that you save time on your project, that you make sure that your netlist is equivalent to your RTL, and that you get the latest and greatest devices out there in the field that we all depend on. So thank you very much for your attention. We would be very happy to take your questions now. My colleague Neil Rattray and I are in the chat or in the audio window, whichever you prefer, and we will be supporting you during your 24-hour endeavor online if you need help with applying our tools and methodologies to your particular issues in the hackathon. So good luck with the mission to Mars. May the best team win. And of course, OneSpin will have a prize for this. More on this in our Discord channel, so please visit us there. Thank you.